Before 2015, watching video on the internet was highly predictable. You clicked a link, a server sent you a file, and you watched it on your own time. This asynchronous viewing created steady, manageable traffic models. Live video synchronized the audience's behavior. Instead of staggered views, millions began hitting the same servers at the exact same moment, a demand standard systems weren't built to handle. Suddenly, engineers had to solve two conflicting problems simultaneously. First, they had to prevent the sheer volume of synchronized viewers from crushing the servers. Second, they had to eliminate the transmission delays that ruin real-time interaction. Adding more hardware is a limited solution. Building a system that maintains massive global scale and near zero latency requires rethinking how data moves across the network entirely. To understand the volume problem, look at what happens when a major public figure, like actor Vin Diesel, starts a live broadcast. Millions of followers receive a push notification at the exact same time. When millions of devices click play simultaneously, it triggers a catastrophic, localized server stress event. Engineers call this the thundering herd. It is effectively a massive, self-inflicted, distributed denial of service attack. If you allow that stampede of requests to travel directly to the core streaming servers, the origin point overloads and the entire broadcast infrastructure collapses. The first line of defense is a global network of edge caches. These are proxy servers physically located closer to the users, designed to intercept video requests before they ever reach the central origin server. The proxy checks if it already has the requested video segment. If it does, it sends it right back to the viewer. If it doesn't, a scenario called a cache miss, it forwards a single request back to the origin server to fetch it. Under normal conditions, edge caches intercept about 98% of traffic. But at live scale, even a tiny leak is fatal. If 1 million people request a video segment simultaneously, a 1.8% failure rate means 18,000 requests bypass the cache at once. Relying on a percentage-based safety net when dealing with millions of concurrent viewers guarantees a system crash at the origin level. The cache has to be absolute. To stop this leak, engineers implemented a software logic called request coalescing. When the thundering herd hits, the edge cache registers a miss for the very first viewer request and sends it to the origin. But for every simultaneous request that follows, it springs a trap. It places those concurrent requests into a holding queue. The origin server processes the single request and sends the video segment back to the edge node. The edge node saves the segment and then instantly clones and serves it to every single request trapped in the queue. Request coalescing rewrites the rules of scale. The origin server only ever processes one request per location, which renders the sheer volume of the thundering herd irrelevant to the core infrastructure. But protecting the servers is only half the problem. When regular people use live streams to talk to a small group of friends, the primary enemy shifts from volume to latency. The standard Internet Video Protocol, HLS, relies on a pull model. The phone constantly asks the server for the next chunk of video, and the server replies with large 3-second blocks. This constant asking and waiting introduces a multi-second transmission delay. To eliminate the lag, engineers abandoned the pull model entirely. They turned instead to the real-time messaging protocol, or RTMP, establishing a persistent connection between the server and the phone. With this line open, the system switches to a push model. Instead of waiting for the phone to ask for large chunks, the server aggressively shoves microscopic 64-millisecond slices of interleaved audio and video down the pipe, shrinking the data packets to a fraction of a second and changing the directional flow from pull to push reduced latency by a factor of 5. This stripped the awkward pauses out of the broadcast, allowing for real-time human conversation. When Facebook rolled out live video to its entire user base, the system held. The infrastructure successfully supported millions of simultaneous viewers while maintaining near zero latency for interactive streams. It achieved this through intelligent traffic queuing at the very edge of the network to absorb the load, and microscopic data pushing at the protocol level to eliminate the lag. Ultimately, true scale at this magnitude depends on re-engineering the mechanics of how data moves through the network.